Okay, today in IM1 we're going to talk about linear functions. So before we go on, I'm going to remind you that a function is a relation for which each x has only one y, or each input has only one output. Okay, it also would pass the vertical line test. And now we're going to look at linear. Linear means that resulting graph is a line, and it can also be written in slope-intercept form, which is y equals mx plus b. So here's an example of one of those. This is on page 67 in your journal. So here's the equation, y equals x plus 3. They did an input-output table for you. So they plugged in -1. -1 plus 3 is 2. That's how they got the output. They did the mapping diagram, which we don't use a lot. They did a nice graph for you. Notice that your y-intercept is 3. Okay, and our slope, which is the line, remember y equals mx plus b. This is your slope. So in this one, my slope is 1. We have to make it a fraction, so it's going up 1 over 1 each time. And so that's the slope, and the y-intercept is right there at 3, so you can see that right there. So this is just the different representations, and they have this way of wording it. An output is 3 more than the input. Okay, so on page 64 in your journal, they give you a rectangle, and they say that the length is 2x and the width is x. And then they want you to complete a t-chart and compare, and we're not going to do all the details of the work, but they want you to compare the x, which is what x would be, 1, 2, 3, 4, and then they want you to compare the perimeter. And they want to know, is this a linear function? So I want to show you that the giveaway is in the formula. Okay, so the perimeter of something would be 2 times the length plus 2 times the width, and that would equal the perimeter. So we would multiply that out. We'd get 4x plus 2x equals our perimeter, or 6x equals the perimeter. As long as this can be written in slope-intercept form, which perimeter, let's say our perimeter is y equals 6x, this is slope-intercept form, this is going to be linear. Whereas the second one, they're giving you x equals the length of the side again, but they want the area. So we know the formula for area is length times width, so that's going to be 2x squared. And that cannot be written in slope-intercept form because there's an exponent. So if you look at the two graphs, you can see that this one is linear, A is linear, and B is not. It's going to go up at an exponential rate. Okay? So the next problem they give you is on page 65, and they're asking you to compare the radius to the circumference. So if the radius, we know that the circumference is 2 pi r. So that right away, we can see there's no exponent. It's going to be a line. Okay? But when you talk about the radius to the area equals pi r squared. And again, this tells us that it's not going to be linear. So again, look at the graphs. This one is linear, and this one is nonlinear. So the equation is the dead giveaway as to what will be linear and what will be nonlinear. When you have an r with no exponents and r is in the numerator, then it will be linear. Okay, so this is the vocabulary that's on page 66. If I was you, I would pause here and write down these definitions because I think they're very helpful. So when you see a linear equation in two variables, they're usually referring to x and y, and it can be written in the form y equals mx plus b, which is your slope-intercept form of a line. Okay, and when it says slope-intercept, it's talking about the y-intercept. A linear function is a function whose graph is a non-vertical line and has a constant rate of change. The function being the word, the main word, and we know that a vertical line is not a function, so that's what it means by a non-vertical line. Any other line is a linear function, and it has a constant rate of change. A nonlinear function does not have a constant rate of change. All of these are nonlinear functions. Examples. Solutions of a linear equation in two variables. They're just saying a solution would be any ordered pair that makes the equation true. So we're talking about the points on the line. Those are the solutions. A discrete domain is a set of points. It means that the values in between are not solutions. Okay, and we'll talk about these more as we go on. And then a continuous domain is that every point on the graph is a solution of that line or that equation. So push pause if you want to write those down. Okay, so this is just showing you that these are not linear equations because x is multiplied by y. This one has an exponent other than 1, and this one, y is in the denominator. So all of these would keep them from being linear equations. Okay, many stretches on the German Autobahn have a speed limit of 120 kilometers per hour. If a car travels continuously at this speed, this equation gives the number of kilometers y that the car would travel in x hours. So they made a t-chart and they plugged in the value of, okay, so if we plug in 1, we get the value of 120. If we plug in 2, we get 240. Notice that x is our hours that we're traveling and y is the distance, and it's going to be linear. It is a straight line. It's a linear equation. It passes the vertical line test, and each x has only one y, and therefore it's also a linear function. Think about it. Okay, so linear equations and their graphs. For any linear equation in two variables, all the points on the graph are solutions. So that means that this point is a solution, and this point is a solution, and this point is a solution, and if I keep my graph going up, this point is a solution. All the solutions to the equation appear on its graph. The arrows mean the graph keeps going on. So there are solutions way up here and way down here. That's what we put the arrows on for. For any 2 points, there is exactly one line that contains them both. This means that you only need 2 ordered pairs to graph a line. However, graphing 3 points is a good way to check that your line is correct, because if you accidentally graph one incorrectly, you'll know that it doesn't match up all 3, and you'll know that one of your points is incorrect. So 3 points is best. Okay, so if we were going to graph this, we would plug in 2 times negative 1 plus 1 would be negative 2 plus 1 is negative 1. Plug in 0, we go 0 plus 1 is 1, and we plug in 1, and we get 2 plus 1 is 3. Then we put those points on our graph, and we draw our line. Okay, sometimes solving for y first makes it easier to generate ordered pairs using values of x. That's not always true, but sometimes it's true. Okay, so this is one of those equations that we definitely want to solve for y, rather than plug the things into x without it. So, the first thing I do is move anything that's not attached by multiplication or division to the other side of my equation and get y and its coefficient alone. I'm going to keep things in slope-intercept form. Now I'm going to divide off the coefficient of y. Remember that when you divide that off, you have to divide every term by the same number. A term is divided by a plus, a minus, or an equal sign. So that means we divide the negative 15x and the 9 by 3. And we get y equals negative 5x plus 3. Now we're ready to solve. X is always on the left. And the y, we plug in the x value. So we go negative 5 times negative 1, which is positive 5, plus 3 is 8. Then we plug in the 0 for x. We get negative 5 times 0 is 0, plus 3 is 3. And then to find y here, we go negative 5 times 1 is negative 5, plus 3 is negative 2. My next step would be to graph my points and then draw my line. And I can see that this is represented by a function. We know it's a linear function because it's in the slope-intercept form, and it passes the vertical line test, so we know that it is a function. Okay, so when we do this one, we have to look at this. When we see a graph that says x equals negative 2, it means that x is always negative 2, but it doesn't tell us what y is. So we're just going to put some random numbers in for y. Okay, so I'm going to put x is negative 2 and y is negative 1. That goes there. X is negative 2 and y is 0 goes there. And x is negative 2 and y equals 3 goes there. And we start to see a pattern. We know that when we see x equals a number, that is a vertical line. Okay? X equals any number is a vertical line. So there's 3 points that they graphed, and the line looks like that. And we can see right away it is not a function because it doesn't pass the vertical line test. And this one x has 3 different answers, and actually has infinite different answers. Okay, now they're going to ask you to, without graphing, to tell whether each of these points is on the graph. So we don't know what the graph looks like, but all we have to do is plug those values in to see if it works. So we go 2 times our x plus 5 times our y, and we're asking, does that equal 16? Well, that's 6 plus 10, and yes, it does. So this is a point on my line. Okay, then I'm going to plug in this one. 2 times 2 plus 5 times 2, does that equal 16? Well, that's 4 plus 10 equals 14, which does not equal 16, so no, that is not a point on this graph. So plug in the next one. 2 times 8 plus 5 times 0. Again, we're asking, does that equal 16? 16 plus 0 does equal 16. So the answer is yes. 8, 0 is also a point on our line. Remember, there are infinite points on every line. So we have to check each one to see if it's one of our points. Okay, so I want to go over some of the restrictions. So, for linear functions whose graphs are not horizontal, the domain and range are all real numbers. And we can see this because the lines represent all the values of x that are going to be covered and all the values of y that are going to be covered. A horizontal graph has a domain of all real numbers as well, and we can see that by this graph, but the range is restricted to the value of y. So the equation for this graph right here is y equals 5. And so our range is y equals 5. It isn't represented by any other number. So it's important to understand that about the range of a horizontal line. Other restrictions occur by our limits of the real world. The domain and range has to be restricted by the quantities that are given. So for example, in our Autobahn problem up in front, the distance has to be restricted to positive numbers. We don't have negative distance. We don't have negative growth periods for babies or months on the cost of our cell phone. Dollars don't go into the negative value unless we're talking about bank accounts. But when we're talking about costs, it's always positive values. And when we talk about the baby's length, it's only positive values. So we have to have restrictions in real world situations. So Okay, this is an example of that kind of a graph with restrictions. And I know there are many different formulas for calculating your dog's age in human years. But we're going to use this very basic one, which is y equals 7x, which means for every year your dog lives, you multiply by 7, and that gives you the human years. So if we go down here to our t-chart, at 2 years old, your dog would be 14 in human years. So he's in puberty, okay? At 4 years, your dog is now 28. So he's in that age range. And then when the dog is 6, he's 42 in human years. So that can help you understand how your dog is aging. So we put those points on our graph. And in this graph, it's appropriate to draw a line because your dog is alive at 2.5 years, 3.5 years, but we just don't have the exact numbers for it. So any point on the line is a solution in this situation. The arrow shows that the trend continues. Your dog continues to age according to this formula, and your dog is alive at these in-between times. Okay. Other restrictions come when you have to be restricted to just points. For example, a quantity such as the number of people can only be whole numbers. When this happens, the graph is not actually connected because every point on the line is not a solution. However, you can see that these graphs are shown connected because you're trying to show the trend. So this is an example. If you're talking about candy bars, you can't buy half candy bars. This is the fee for overdue books. They only charge you by the days, not by the 1.5 day or the 2.5 days. It's just by days. So here's an example of. Okay, so this is that type of an example. At a salon, Sue can rent a station for $10 per day plus $3 per manicure. So if you look at the equation, the $10 is a one-time fee, so we put it once. The per cost, which is the cost per manicure, is the 3 times x. Now, an important thing to remember is right now, this is just talking about her costs. It's not talking about how much she charges. This is her rental payment, okay? So that's all we're figuring out for her. She uses this to figure out what she's going to charge so she can cover her costs. But that's more complicated than what we're dealing with right here. So this is what she's going to pay for a rental. So let's say she did 2 manicures, okay? We would plug the 2 in. We get 6 plus 10, which is $16. And that one is represented right there. Okay, now if we look at this, we could also draw the line connecting them, but it's important that we understand that the individual points are the solution in this situation. She's not going to do a half manicure. Okay, she's only going to do complete manicures. So the line in this case shows that the trend continues, but only the individual points are the solutions. So, evaluate each linear equation. Is it a function? The easiest way to do this is to solve for y. So I'm going to subtract x to the other side. I get 2y equals negative x plus 6. Divide by 2 every term, and I get y equals negative 1/2 x plus 3. Since it's written in slope-intercept form, I know that it's linear, and it is also a function. Okay, for this one, I'm going to divide by 3, and I get y equals 4, and that is a horizontal line, and horizontal lines are also a function. So the answer is yes for both of these. Okay? And there's your graphs. All right. Okay, these are a couple of problems from the book just to give you an idea. When you're deciding if something is discrete or continuous, you look at your x values. So I'm talking about the bags, and how many marbles I can put in the bags depends on how many bags I have. So since I'm limited to whole bags, okay, I can't have a half bag and put any marbles in it, then this is a discrete example, a discrete graph, because I don't have half bags. I can only put marbles in whole bags. Now let's look at this one. It's saying that their answer is incorrect. So again, I'm going to look at what are my x values. They are 1, 2, 3, 4, 5, and 6. So that means 2.5 is not in my domain because my domain is 1, 2, 3, 4, 5, 6. So now that we've finished, this is the end of the slide. So make sure that you understand these concepts before you go on to do your homework. Take care.